The number one reason a local AI model runs painfully slow is embarrassingly simple. The model does not fit on the graphics card, so it spills over onto the CPU and everything crawls. And almost nobody checks this before they download. They grab a model, it runs at a few words per second, and they conclude their hardware is too weak or local AI is a waste of time. It usually is not. They just pick the model that does not fit. I size every model against my card before I download a single gigabyte. And I want to teach you the simple arithmetic so you can do the same. No trial and error. Let me start with the one resource that decides everything, VRAM. That is the memory built onto your graphics card itself, separate from your regular system memory. It is fast. It sits right next to the part of the GPU that does the math, and there is not very much of it. A typical gaming card has 8, 11 or 16 gigabytes. That number is the hard ceiling on what you can run well. The whole game is predicting whether a given model will fit inside that ceiling, because when it fits, it flies, and when it does not, it stalls. There is no middle ground that feels okay. It is fast or it is slow. So what actually has to fit in VRAM? There are three things, and most guides only mention the first one. The first is the model weights themselves, the giant pile of numbers that is the model. The second is the context, which is the memory the model uses to hold your conversation and whatever text it is working on right now. The third is overhead, the working scratch space the system needs to actually run the computation. If you only budget for the weights and forget the other two, you will load a model that technically fits. Then watch it spill the moment you give it a long prompt. All three have to live in that same limited memory at the same time. Let me give you the formula for the weights because it is the big chunk and it is easy. Take the number of parameters in billions and multiply by the bytes per parameter. At full precision, that is 2 bytes per parameter. So a 7 billion parameter model is about 14 gigabytes just for weights. That does not fit on most cards, which is exactly why we quantize. At 4 bits per weight, you are at roughly half a byte per parameter. So that same 7 billion model drops to around 4 gigabytes. The quick mental shortcut I use is this. A 4-bit model takes roughly half a gigabyte of VRAM per billion parameters. So 7 billion is about 3.5 to 4. 13 billion is about 7. That one rule of thumb gets you 90% of the way. Now the part people forget, the context. When the model processes text, it builds up a working memory of everything in the current conversation, and that memory grows with how much text you feed it. A short question costs almost nothing. But if you paste in a long document or you have a very long back and forth, that working memory can balloon to gigabytes on its own. This is why a model that ran fine on short questions suddenly chokes when you give it a big input. You did not change the model. You grew the context and it pushed the total past what your card holds. So when you budget VRAM, you cannot fill the card to the brim with weights. You have to leave room for the conversation to grow. Here is the practical way I handle that. After I estimate the weight size, I leave a buffer on top, usually a couple of gigabytes minimum, more if I know I will be feeding it long documents. So on my 11 gigabyte card, I do not look for a model whose weights are 11 gigabytes. I look for one around 7 or 8, leaving 3 or 4 gigabytes of headroom for context and overhead. That buffer is the difference between a setup that stays fast all day and one that mysteriously gets slow whenever you give it real work. People who skip the buffer are the ones who post that local AI is unreliable. It is not unreliable. It is just full. Let me walk a couple of real examples end to end so the math feels concrete. Say you have an 8 gigabyte card. A 7 billion parameter model at 4 bits is about 4 gigabytes of weight. Add a couple of gigabytes for context and overhead, and you are around 6. That fits comfortably with room to spare, so it will run fast. Good choice. Now say you eye a 13 billion model at 4 bits, about 7 gigabytes of weight. Add the buffer, and you are already at 9 or 10 over your 8 gigabyte ceiling. that one will spill and crawl. So on an 8 GB card, 7 billion is your comfortable home and 13 billion is a stretch you should avoid unless you compress it harder and accept the speed hit. One more example, because the bigger cards change the picture. On a 16 GB card, that same 13 billion model at 4 bits, 7 GB of weights plus buffer fits comfortably and runs fast. You could even reach for a larger model or run the 13 billion at higher precision for better quality. This is the real reason VRAM is the spec that matters most when people ask what to buy for local AI. It is not the raw speed of the card that limits you first, it is whether the model fits at all. A slightly slower card with more memory will run models that a faster card with less memory simply cannot load. Let me make the spilling cost vivid, because understanding it changes your choices. When a model does not fit in VRAM, the system does not refuse to run it. It quietly moves part of the model into your regular system memory and runs that part on the CPU. The problem is that the CPU and system memory are dramatically slower at this work than the GPU. So even if only a fraction of the model spills over, that fraction becomes the bottleneck and your speed can drop from comfortably fast to 10 or 20 times slower. It is not a gentle slowdown, it is a cliff. This is why fitting matters so much more than people expect. Being slightly over the limit is almost as bad as being way over it. Now let me save you from a trap. The file size you see when you download a model is a good first estimate of the weight memory, but it is not the whole VRAM cost. The file is just the weights on disk. Once loaded, you still pay for context and overhead on top. So a 4 GB file does not mean 4 GB of VRAM. It means 4 GB plus your context plus overhead. Treat the file size as the floor, not the total. If the file alone is already close to your card's capacity, that is a clear signal to step down to a smaller model or a more aggressive compression, because there will be no room left for the actual work. Let me put real numbers on the context cost, because the rule of thumb only goes so far. The memory the context uses depends on the model and grows with how much text you hold. For a typical mid-sized model, a short conversation might use a few hundred megabytes, barely a rounding error. But a really long context, the kind where you have pasted in the large document, can climb to a gigabyte or several. That is why a model that loaded fine and ran fast suddenly chokes the moment you feed it something big. The weights did not change, but the context ballooned and pushed the total past your card. So when you plan, picture not just the model at rest, but the model working on your largest realistic input. That worst case is what has to fit. Let me handle a common question. What about running two graphics cards? Because people reach for this. You can split a model across two cards and their memory adds together. So two 8 GB cards can run a model that needs around 16. That is a genuine way to run bigger models at home. But be honest about the catch. The cards have to talk to each other constantly while running the model, and that communication adds overhead, so two cards are not quite as fast as one card with the same total memory would be. Still, for fitting a larger model that no single card you own could hold, splitting across two is a real and useful option. Just do not expect the speed to scale perfectly with the memory. Let me give you the honest version of how system memory fits into this, because it confuses people. You have VRAM on the card, and you have regular system memory, the normal RAM in your computer. Those are separate, and only the VRAM is fast for this work. The reason it matters is that when a model does not fit in VRAM, it overflows into system RAM and runs the overflow on the CPU, which is the slow path. So having lots of system memory does not make your models fast. It just lets the slow overflow happen instead of failing outright. People see they have plenty of regular RAM and assume they can run big models. They can, technically, but slowly. The fast capacity is only the VRAM, and that is the number that actually governs your experience. Let me make the buying advice concrete, since this math is exactly what should drive a hardware decision. If you are choosing a card specifically for local AI, The amount of VRAM is the spec to prioritize ahead of raw speed. A card with more memory runs models that a faster card with less memory simply cannot load at all. A used card from a previous generation with a generous amount of memory is very often a smarter buy for this than a newer card with less. And the jump from 8 to 12 to 16 gigabytes each unlocks a meaningfully larger class of models. So when you work through this math and feel the limits of your current card, the upgrade that helps is the one that adds memory, not just the one with bigger benchmark numbers. Let me give you a quick mental table you can carry around because this is the practical payoff. On 8 gigabytes, you live comfortably in the 7 to 8 billion parameter range at 4-bit compression, with room for normal context. On 12 gigabytes, you can reach mid-sized models comfortably and run the smaller ones at higher quality. On 16 gigabytes, the 13 billion class becomes comfortable and you have real headroom for long context. Above that, the larger models open up. Memorize roughly where your card sits on that ladder, and you will instantly know whether any model you come across is in reach, without doing the full arithmetic every time. The math is the foundation, but the ladder is what you actually use day to day. There is one more lever worth knowing about, and it is the context length setting. Many tools let you cap how much context the model is allowed to use. A smaller cap means less memory reserved for context, which frees up VRAM. So if you are right on the edge of fitting, dialing the context limit down can be what makes a model run smoothly instead of spilling. The trade-off is that the model can then handle less text at once. But for a lot of everyday tasks, you do not need a huge context, so trimming it is a free win. It is one of the first knobs I reach for when a model is almost fitting but not quite. So here is the whole method in order. Find the model's parameter count and its precision. Estimate the weights, roughly half a gigabyte per billion parameters at 4 bits. Add a buffer of a couple gigabytes for context and overhead, more if you feed it long documents. Compare that total to your card's VRAM. If it fits with room to spare, it will run fast. If it is over, step down a size or compress harder or cap the context and check again. Do that arithmetic before you download, and you will almost never be surprised by a model that crawls. This is the boring math that separates a local setup that just works from one that fights you constantly. It is exactly the kind of unglamorous detail I cover on this channel, real working systems with the honest trade-offs spelled out. If that is your thing, subscribe and follow along. Subscribe for more AI builds.